Pendulum problems. Yay, physics!
You're getting.
Okay. You can see you're all getting very sleepy. Ah. So, pendulum is released and allowed to swing back and forth. The periodic nature of the pendulum is modeled by trigonometry. Who would have thought?
How do you know that you're getting very sleepy?
Because I know you guys.
Did you go into the future and then?
Yeah, time traveled. I definitely time traveled.
That's crazy.
Okay, so the period, sorry, not the period, the horizontal displacement in centimeters depends on the time that's gone on. Right, so you take a pendulum, swings back and forth. Realistically, though, it doesn't go on forever because of friction. It loses energy and eventually stops. Right? That's kind of one thing that you've been ignoring your whole physics life, unless you've taken Physics 12. Is a lot of the equations that you use to model pendulums or pretty much anything. There's some things that you're ignoring, so your equations are unrealistic. And if we just left it at this pendulum would swing back and forth forever and never lose energy, never decrease in its horizontal displacement. Right? So that's where this other guy comes in, Q. Okay, it's a decay of the amplitude, a decay of how far it's going away from the resting position. So we're going to write a combined function that's the product of the two components and explain what happens. Okay, so let's make a new function. Let's just call it R. And we're going to combine P and Q with multiplication. So we get 10 cosine 2t times 0.95t, or 0.95 to the power of t, I should say. And there's not really any simplification that you can do. In fact, I would I'd probably leave it at that. You might put 0.95t in front, and then go 10 times cosine 2t. The only caution I would say is that you cannot combine 0.95 and times it by 10. You can't do that.
Where's G?
You guys clear on that? Oh, I put G in there. I meant Q. Sorry. Yeah, you can't go 0.95 times 10 and just leave it to 9.5. It doesn't work. Okay? 10 does not have the same exponent as 0.95, so you can't combine them. So this is as far as we can go. Okay? So I want you guys to graph this and just kind of look at what happens. What do you think will happen? What do you think it'll look like?
It's just gonna kind of.
Okay, so let's graph it. So 0.95 to the power of x. And 10 cosine 2t. Oops, that's 11. Or 2x. And make sure you're in radians. And a window, let's start with zoom 6. What? Let's make it go out a little further, maybe 50 seconds. What?
That's cool.
Pretty cool, eh? So you can see this wave models the amplitude, how far away the pendulum is from where it started. Right? But because of friction in the pendulum thingy that it's attached to, and also air resistance, that would factor in as well, it gets smaller and smaller and smaller. How far does it need to go before it basically gets to zero? What do you think?
62.
Let's say it's pretty much stopped by the time it hits 0.1, what would it be, centimeters? Yeah, 0.1 centimeters away from equilibrium. When does that first happen? 95 seconds?
I'm gonna go with 75. 80. 80. Let's go 80.
Find it. See if you can find it. When it's 0.1 centimeters away from equilibrium. So I'm going to go negative 0.5 to 0.5. And let's make this go out a little further. See if I can still see it. Interesting. A little more. So it looks like it's happening around here. Wait, where's 0.1? Let me put that in. So about here. So that's, what's my window, 80? No, 100. So let's go like, let's try 70 to 80. See how that works. No, a little more. 70 to 90. Hey, you're a window range. Yes. Notes. Oh, we're almost there.
95. 96.
96?
96.
Boing, 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 boing. So it looks like about here is when it's hit its maximum of 0.1. What is that? Yeah, it's just less than 0.1, so it's 91. Ha! Beat you.
Whatever.
Good? Pretty cool, eh?
Same can be used to model the vibration in my gauge strings.
Yep. There you go. Every time you play music, you're doing trigonometry and exponential functions and product of functions